Hello everyone, welcome back. Here's vanAmsen. Today we are going to solve a very intriguing programming task. Minimize the maximum difference of per 2616 from LeetCode. So trust me, you are going to want to stick around for this. Alright, so let's dive right in. Here's our task. Given an array of integer and a number p, we need to find p pairs in this array. But here is the catch. The maximum difference among this pair should be as small as possible. So let's break down the first example. So we are given an array of values. So on the left are values 10, 1, 2, 7, 1, and 3. And p is 2. So how can we form the pairs? Now observe that with the smallest difference are 1 and 1, green 1, and the difference is just 0. And the next smallest difference is 2 and 3 with index 2 and 5, so red 1, and difference is 1. So we return the maximum of minimum differences, so in this case 1. But imagine if p will be 3, so then we need to return 3. Why this? Because third pair will be created from index 0 and 3, so it's 10 minus 7, and 10 minus 7 is difference 3. So then we return the 3 because it's next minimum pair. Okay, so now when we understand the problem, our goal here is to ensure the maximum difference among all pair is minimized. So, and the answer is the difference of our largest pair. So now how to do and solve it programmatically. Binary search and greedy approach. So instead of searching for a specific value in array, we will use it to search for the smallest maximum difference. So here's our main function minimize max, and we will be sorting out nums array, and then we will define our binary search boundaries. So left will be at 0 and right will be at difference between the maximum and minimum value. Okay, so we will implement it in Rust. So num sort, and let mutable left will be 0, let mutable right will be numlen minus 1, so maximum element minus num at 0, so minimum element, because we already sorted our array. And while left less than right, left will be mid will be left plus right divided by 2 without remainder, and if solution function can form pair. So we will implement it later. So num, mid, and p. And right will be mid, and else left will be mid plus 1. So close the bracket. Okay, so all right, the real essence of our solution lies in the logic of these two loops. So let's see it. So the outer loop is our implementation of binary search. Instead of using it to find a number, we are using it to pinpoint the smallest maximum difference between our pairs. And our search space starts from the left beginning of 0 and right as the difference between the largest and smallest number in our sorted array. And this is because the maximum possible difference is between these two extreme numbers. So within the loop, the midpoint, mid, represent a potential maximum difference. Think of it as a guess. And we are asking, can we form p pairs where the largest difference is at most mid? So that's why we put array of num, mid, and p. So to answer that, we use can-form per function that we haven't implemented yet. So in this function, we return true, and it means we can indeed form the pairs, and our meet value is a variable answer. But we don't stop there. So even if it's possible to form the pair with this meet, we want to check if there is a smaller meet that works. So we adjust our right boundary to meet to explore a smaller value. However, if we can't form the pair, our guess is too low. So we need a larger meet. So we move our left boundary to meet plus 1. And now let's dive deep into can-form pairs. So this function check if we can form the required p pairs with a maximum difference of meet. So let's implement it. Left, yep, so we return left in our minimize max function. I don't know why we have this. Okay, so now let's try to implement our second function, can form pairs. So fn can form pair num vector of i32 meet i32 pi32 and return boolean and let mutable count and let mutable I be 0 and while I num len and count less than p, if num I plus 1 minus num I less than meet, then count plus 1 and I plus 2, and else will be I plus 1. And finally return count greater than p. Okay, so it's our boolean value. Yeah. And also we need to make it mutable. Okay, so now we can try to run it. Hopefully it will work. So yeah, all working as expected. Awesome. So within our loop, if the difference between two consecutive numbers is less than or equal to meet, it means they can form one of our pair. So we increase our count, and now remember we can't use an element more than once. So that's why after finding a pair, we skip the next element by increasing I by 2. So if they don't form a valid pair, we simply move to the next element. And finally, after the loop ends, if our count is greater than or equal to p, it means we have successfully found our pair with a maximum difference of meet. So this loop work in tandem. So the outer loop refines our guess using binary search, and the inner loop validate our guess. So understanding these loops is key to grasping the essence of this solution, and it's where binary search meets Perling logic. So that's it for today loops, a beautiful blend of logic and algorithmic with binary search and greedy approach. And yep, so let's run it for unsynthesized cases as well. So they are probably more tricky, but we have successfully solved this code, and our implementation beat 100% with respect to runtime and memory, and it took just 14 milliseconds. So all good. And yep, that's it. Once our binary search is done, we have our answer. So binary search isn't just a searching, it's a powerful tool to solve a variety of problems, and I hope this solution gave you a new perspective. And yeah, if you found this explanation helpful, give it a thumb up and share it with your friends for more intriguing coding problem and daily tutorials and much more. And make sure to subscribe to the channel, and don't forget to code in other languages is provided in the description below. Happy coding, see you next time.